So welcome back for the last session of the day. So in this session, we have 6 speakers, starting with Ramkishor Sharma, and he will be talking about probing Axion-U inflation. So over to you.
Okay. Hello everyone. I think I'm audible at the back. Yeah. Okay. First of all, a big thank you to the organizer for giving this opportunity to talk about this recent work of mine. It's also a quite new topic for me. So what I will be talking about is like a phenomenology of the Axion-U inflation, which can also be used to constrain a coupling between Axion and U1 field. So as an outline, I will just quickly, just for the completeness, will give you an introduction to the key epochs of the early universe, and then tell you about what is the observational status of the Axion inflation, and then we'll move to the Axion-U inflation and give you some results from the previous literature, and then we'll talk about our recent work where we did perform some net simulations to explore the back reaction regime of this, and then comment on what has been changed from the, let's say, previous literature, what more we can say about this observational status of this model, and then we'll summarize the talk. So it's a brief history. We believe that our universe started with an exponential expansion of space, which we called inflation, and we don't know what causes an inflation. Even a famous cosmologist, Tordelson, writes in his book, saying that whoever will find the origin will be a next candidate for the next Nobel Prize. And so whatever causes inflation decays to all the standard model particles and even to the dark matter particles. We heat the universe to a very high temperature, and that's called a reheating epoch. And at this epoch, universe is already at a very high temperature, highly ionized. And as we go further in time, universe expands and pass through various key epochs. Like when the temperature is around 100 GeV, then there may be a electroweak phase transition. And if it's first order that we have been hearing during this conference. And then if the temperature reaches around, let's say, 1 MeV, then there will be first time nuclei will form. And when the temperature reaches roughly around 0.3 eV, that will be the first time when the universe transits from the ionized state to the neutral state, and photon will start travel freely and will reach us in the form of microwave background. And that's before that universe was ionized, there was no direct photon coming to us. So before this epoch, whatever I say is the early universe for me. So how can we probe this? First question comes to your mind, why photons? And then the photons I told you is only coming from this surface. So whatever we can see, it's only by some indirect imprints on this surface, and there has been many talks about that, and we have heard like how we can probe this. So and the second candidate will come. It's can be neutrinos, since neutrinos interact weakly. So we expect there will be a similar background of neutrino, but they are very low energy neutrino, and we don't know if we can detect them in future. But let's be hopeful. And the recent discovery of gravitational waves now have opened a new era, let's say, for astronomy, and also now there are efforts to observe gravitational waves in various bands, and which can be used now to probe also various key epochs of the early universe. So to give some little bit more details, so if I change this picture to this picture where I have these key epochs and also gives you the horizon size at these key epochs, basically if there is a source which can generate gravitational waves, and if it's a causal process, it cannot exceed this horizon size. So what the peak will be below that scales. So if you see, these scales are roughly around 100 GeV will be this much, and 150 eV will be around parsec. So if you look at CMB and look at the resolution of the Planck satellite, that is roughly 5 arc seconds. So it will project a scale of roughly 10 megaparsec. So you can get an idea. To probing these epochs, there is no way to probe, let's say, a phase transition via some looking at the photons. But if you change this picture to the frequency, and then you will see that gravitational waves can provide us, if we can detect some gravitational wave in the future, let's say in millihertz band, that will probe an epoch like around electroweak. And there has been talks on that, and also like if you look at very early universe like inflation, which obviously can leave signatures from a wide range of scales and can be probed by beam modes and all. So I also thought I will just briefly give rough estimates, although in the morning and also in previous talk it has been given some rough estimates to realize that how hard it was to detect the gravitational waves. So this is an estimate for a binary mass system. So this equation we have seen, and if you just solve it in the far, let's say if your observer is far from the source, and same analogy from the electromagnetic theory, you will get such a solutions where Ik is a quadruple moment. If it would have been electrodynamics, and there would have been moments of the charge density instead of the mass density. So if you look at this binary mass system, if you look at what are the parameters in the picture, distance of the distance from the observer, the masses of the two bodies, and then what are the frequency at they are rotating, and then the distance. And you just put in this formula. And what I did further, I just tried to put some numbers of the first LIGO events, which they have did the gravitational wave, and turns out to be 10 to the minus 21. So basically, this will be the change in your arm lengths of the detector. So that's, if you see the numbers here, this is the plot from the LIGO scientific collaboration paper, and you see this number are roughly of that order. So however, in cosmology, it's not like a point source event, but let's say some process happens, some electroweak phase transition or any other source, it will be coming from everywhere. So distance of that source doesn't make a sense, since it will be balanced by the area, the 4 pi r square factor, since it's coming from each direction. But we have expanding universe. So to balance that, one usually quantify things in terms of this parameter omega GW, which has also been defined in earlier talks. But what you do, you can write it in terms of the total radiation budget. And since we are talking about early universe, we will be quantifying things in terms of the energy budget at that moment, and it's mostly radiation dominated. So you can find like this quantity will usually depends on the square of the energy budget of the source to the total energy budget. And there is one more scale which comes into picture, where basically the source, basically let's say if these are scalar inhomogeneities, which source is the production of gravitational waves, where does it peak? So if it is very inside the horizon size, then there will be a suppression, roughly typical suppression by this factor. But although it also depends on the detail, what is the source, and there can be additional things coming up. But this is a simple expression. You can estimate what will be the typical amplitude of the gravitational wave produced or source in the early universe. So with this, let me move to the topic of this seminar. So one of the model of Axion of the inflation is Axion inflation, and this was proposed in 1990s, and this has it's also with the name of natural inflation, since it's naturally protect the flatness which we require to explain the observations. But however, if you look at the current status of this model, it is rolled out by even more than 2 sigma level. So if you look at this diagram, this figure, this is from the Planck results, and there are these 2 green lines which are for different decay constant, and if you see, they are well outside let's say the 2 sigma range of different observational data. And what are the difference in the 2 lines? So basically, you are taking that your pivot scale is let's say 50 falls before the end, or 60 E falls before the end of inflation. However, after this, there has been many proposals to make it, let's say, compatible with the observation, and one proposal was by Anber and Sorbo in 2019. What they allowed, let's say, since this is a pseudo-scalar, it can be coupled to a U1 gas field, and if you allow this additional dynamics, there may be a possibility that way it can be a viable model. Let me just emphasize it briefly. So what will happen if you look at now the dynamics of the U1 field or gas field? It can be standard model gas field. So and if you look at neglect the inhomogeneity of the axion, and then look at the equations of the evolution of this gas field, it will take this form. And if you see now, there is this negative sign for one of the mode will get amplified exponentially, and it will be amplified for the modes which are crossing roughly around the horizon side. I forgot to put the where this formula is valid, but this is valid around the horizon size. So you see, this exponential expansion depends on this parameter xi, which depends on the velocity of the axion and also the coupling strength between the axions and the U1 field. So so velocity of the axion will be maximum towards the end. So basically, maximum amplification will be felt by the modes which will be exiting towards the end of inflation. But this can be also earlier, it depends on the coupling strength. So what will happen as this mode this gas field gets amplified? If they are sufficiently amplified, they can back react on the evolution of the axion and provides an additional friction, and can extend the duration of inflation and make it compatible. And this has been, in the recent paper by Koushik and Noor, and I think Koushik will be talking about in detail in a later talk in this session. So it turns out that if you take like a large coupling like around 300 and depends on also your decay constant, it may be it may lie within this present. It may be compatible with the CMB data. So, however, it requires, as you can see the numbers, this requires a very large coupling between axions and U1 field. So once this coupling is large, it also becomes phenomenologically very interesting, and it turns out to be that this phenomenology can be also used to probe this coupling between axion and U1. So basically, idea here is that because of this coupling, you will produce this gas field, but these gas fields can lead to the production of gravitational waves and also can enhance the inhomogeneity of the axions. And if they are large enough, they can also form the primordial black holes. But if you look at this gravitational wave, as I told you that this velocity of the action will be maximum towards the end, so the mode which will be exiting towards the end of inflation will get amplified. So these gravitational waves will be very high frequency gravitational waves. And primordial black hole will also be very light mass. They will be even evaporate before the BBN, and it depends like what is your coupling strength. And this has been taken and this has been studied by various authors in the previous study. And let me, before telling you about the results, let me emphasize this: since this gravitational wave will be very high frequency, roughly let's say in the gigahertz for a Guth scale, around if this end of inflation happens around the Guth scale. So in this for the gigahertz band gravitational wave, the best constraint at the moment we have for the background is only from the ineffective or basically constraint on the extra radiation degree of freedom from CMB. And this gives a constraint roughly around 10 raised to minus 6, which just says that it's just some fraction of the total energy budget of the universe. I want to just quickly fly through the other things. These are the constraints from the looking at the radio background. So basically the process here is that if you have this high frequency gravitational wave, if they pass through some medium which has magnetic field, let's say you have this magnetic field in the intergalactic medium, then they can be converted to the similar frequency radio waves, which will be gigahertz electromagnetic waves, that are the radio waves. So, but the constraint coming from all these, as it's basically no constraint you get at the moment. So best constraint is from the ineffective only. So let me go back now and talk about the phenomenology of this axion and gas fields. So first thing is like these authors have studied the formation of primordial black hole and try to find out what will be the constraint on this interaction between axion and gas field. So what they have considered since the back reaction will be of the form of, since the term is E dot B, so it will be like an E square or B square term. So if your let's say you have this produced gas fields, which are let's say Gaussian in Gaussian random fields, but since the back reaction is of the form E square, so basically the produced inhomogeneities will have a distribution of the chi-square, since it's the Gaussian square. So they have took that assumption and tried to estimate what will be the abundance of the produced primordial black hole, and obtain, let's say, a bound. This alpha by f should be below 130 Planck mass inverse. At this slide, I would also like to just to read my slides. So wherever I have small m, that's the Planck mass, and wherever I have the capital M, that's the reduced Planck mass. And if you want to convert from reduced to reduced Planck mass to the Planck mass number, you just multiply by root 8 pi, which is roughly 5. So since some authors have used this unit, so you may find it a bit difficult, but just multiply things by a factor of 5, and you can easily read those numbers. But this was a one constraint. But if you now look at the produced gravitational waves, which has been studied by these authors, and so basically there are few horizontal lines here. So this is the current limit which I was telling you about from the ineffective on the gravitational waves, and these are the future forecasts. So this already says that for alpha by, so basically for this model, not to overshoot this ineffective constraint, your alpha by f should be below 70 Planck mass inverse. And this is the strongest, there are various other constraints you can get. Basically, you can get also constraint from non-gaussianity, but this is this was the strongest constraint coming on this coupling. However, few things to realize here, since we are looking at a regime where the back reaction of the gauge fields are important, and let's say these studies are basically based on some analytical approximations, and one has to check if all these assumptions are valid and or not. So what we did, I mean not we, there are several groups now doing these lattice simulations of Axion-U inflation. So they are solving these equations on the grid, and for this we use this pencil code and to solve these PDEs. And so let me now focus one by one. So I will start what is the dynamics now what we get from the from the lattice simulations. So what are these three vertical panels? They are for different coupling strength, and for this coupling strength, back reaction of the gauge fields is not important during inflation, but it's only important in the reheating phase. So let me go slowly through this plot. So what you are seeing in different colors. So red color has the potential energy of the axion field, and the yellow curve has the kinetic energy, and the blue is the gauge field energy. So you see, and then this vertical gray line is marks the end of inflation in each corresponding to each panel, where the epsilon, the lower panel, reaches to 1. That's the end of inflation for us. So you see, in this case, this is the usual end when the kinetic energy roughly becomes of the order of the potential energy. However, if you go to larger coupling cases, where the back reaction of the gauge field becomes important even during inflation. So what it does, basically, why gauge fields were amplifying depending on the velocity of the axion field. But once the back reaction becomes important, they reduce this velocity, and then electromagnetic energy takes over. So in this case, end of inflation will be around the epoch when the electromagnetic energy buzzed and the potential energy will be roughly equal. So and that will also lead to the extension in the duration of inflation. If you see, the numbers here are the usual end, the slow roll end of inflation. But now the new end of inflation, once the back reaction is taken into consider, will be enhanced depending on the coupling. So this is a plot for a even higher coupling, and there the end is around the extension in the duration of inflation is by 4 e-folds, in which in this case it was around 2 e-folds. Few more things to mention here. So to check our simulation, what we did, we also did a study where we neglect in our equation the inhomogeneities and only looked at the homogeneous axion case and then look at the total system. And there were already analytical studies, semi-analytical studies on that, and this curve here is plotting this parameter chi, which I was mentioning earlier, related to the velocity of the axions and the coupling strength between axion and U1. So okay, it's not very visible, the white curve is the results from the semi-analytical study, and the green curve here is from our simulation, but in the homogeneous case, and they are on the top of each other. That was a check for us. And then in the inhomogeneous case, this is the full where you include the all inhomogeneities of the axions and all. So you see some differences that earlier there were some oscillations which will also lead to some oscillations maybe in the produced gravitational waves, but once you consider the full case, these oscillations are also suppressed. And this is not just we realize it, it's also done by this group, Fuggerov and et al, and even a year before. And so yeah, so few things to take from this slide. It's like inflation is extended by a certain number of e-folds depending on the coupling strength. And now when the back reaction is important during inflation itself, so end of inflation will be decided by when the energy budget of the electromagnetic or the gauge field is roughly equal to the potential energy of the actions. So now let's look at, together this setup we also solves the gravitational wave equation and taking the source, taking this produced gauge field at the source and also the action inhomogeneities. So what we found here, so these curves are for different coupling strengths. So basically 35 going to up to 90. Okay, that's missing here, but I think last color, which is the blue or cyan, that is for the case of coupling strength of 90. So if you look at, so again, this horizontal line, this is the Planck and effective constraint. These are the future projection by CMBS4 and other missions. So if you see here that earlier studies, they have explored these regimes up to, let's say, this coupling strength of something 60 and 70. This was a bound obtained from the previous literature. But if you look at the case in which back reaction is important during inflation, last two curves, like the curve corresponding to alpha by f 75 and 90, you will find that once the gauge field back reaction becomes important, since now the gauge field growth is also smaller, so gravitational waves growth will also be smaller, and they may not exceed these bounds. However, if you go and keep on running this simulation, let's say even after end of inflation up to the few e-folds, it may exceed. But here one important thing to mention, I mean, since the gauge fields are now, if you look at the gauge field energy density, they are also comparable to the background, and we in this simulation we haven't included any charge field. So, but if you include the charge fields produced due to this gauge field, they may suppress the further production, and then the GW may not exceed these bounds. So basically, these bounds which has been obtained earlier can be relaxed in these regimes of higher couplings where the back reaction is important during inflation itself. So this is first result to see, and then the second thing, as I was telling you, this bound which has been obtained using the formation of primordial black hole assumes this chi-square type distributions. So what I have it here, so we are in these curves, we are showing the PDF of this delta phi, I mean basically the axion field fluctuations at different time during the simulation, and these different horizontal panel are for different coupling strengths. So this is the case when the back reaction of the gauge field is never important. So what you see you start with some Gaussian random field. So basically the blue curve here, which is on the top of each other, it's we're just saying that at, let's say, at the beginning of the simulation is minus 3.1. So n equal to 0 marks the end of inflation. So you start with some Gaussian random field, and then slowly the distribution goes indeed towards a chi-square. However, if you look at the cases where back reaction is important, yes, indeed it goes to chi-square in between, but it start again going towards a Gaussian. It's not the Gaussian at the final limit, but the things to take away from here is like it will have less tail as compared to the chi-square. So the constraint obtained earlier in the previous studies will also get relaxed once you take this new probability distribution. We haven't done this detailed study since this is only 1 point probability distribution function, but we wanted to do it much more detailed. So what we will plan to do is basically we will take on this the distribution of the averaged. Let's say we want to pick this scale, and then we will take the averaged inhomogeneities, and we'll look at the distribution of that. And we expect that the distribution of the averaged or smoothed density will be even closer to the Gaussian. So these are the two things to take away from this, and I would also like to end by mentioning this recent work again by the group A, which they also doing this Axion-U simulation. So they are now trying to find out a relation between this Axion-U coupling strength and how much will be the extension in the duration of inflation. So in this, I mean, numerically you also bound, you cannot go to an arbitrary large coupling strength, since you can only, let's say, do some 1000 cubes, and since your peak of, let's say, produced gauge fields is also moving, once it is out of the box, you cannot trust on your results. So they have gone up to, let's say, coupling strength of 20 in the reduced Planck mass. If you multiply it by, in Planck mass, it will be around 100. And they found these are the typical extension, and they try to extrapolate, and this is the table from this paper, that it can be go up to 20 and all. Why I'm mentioning this, since this will be important to decide the observational status of Axion-U inflation, that how much it got extended. However, there is no, like, and I don't have a final plot to say, like, what is the status, is it observationally viable, but this is to check further by taking some results from these numerical simulations. So to summarize my talk, so Axion-U exhibits this rich phenomenology, and which can also be used to constrain this coupling between Axion and U1. And however, there are few things which one should address, what will be the effect of the charged particles in this scenario. And with this, I would like to conclude. Thank you very much for listening.
So thanks very much, Ramkishor. So time for questions. You can use that mic.
I have a couple of questions.
Yeah, sure.
The first one is the slide before.
Yep.
Since you have, sorry, the next one.
Yeah, okay.
So since you have radiation already present,
Since you have
You have a
radiation.
U1 field present already.
Yes, yes.
So in some sense, you know the full history of reheating in this model.
Yes, that's correct.
So then when you predict your NS and R, instead of doing it for 50 and 60 vaguely, you can do it exactly. Because
Yeah, but
you
basically the idea here is to know how much will be the extension.
yes, for a given alpha, for a
Yeah,
given alpha, if you know extension, you'll have a specific point in the NSR plot.
Correct, correct.
So once you correct for it, do you get it inside the observable,
Yeah,
observationally allowed limit?
Right, right. I mean, Koushik will also talk about it in his talk, but like in their case, they are looking at only the homogeneous back reaction. So for that, they require like this alpha by F roughly around 300 or 200 to make it viable. But numerically, you cannot go that large. I mean, you can do it, but then you can only probe some 10 E-folds. You cannot go until the end of inflation. So it's very hard. I mean, it's not easy to answer at the moment, but yeah. So I don't know.
So one should be careful with the prediction plots.
Yes,
That's what I'm saying. The second one I'll ask quickly.
Yep.
So the second one has to do with the fact that the reason you are producing U1 field is because you have a background which is changing fast. That's all is going on in my understanding. Right?
Yeah, I mean you are producing because this phi
time dependent
decoupling
background,
is there.
right? So, but it'll oscillate. Your axion will oscillate eventually. So that should resonantly produce more. Does that happen? Does it produce more photons?
Okay, for that, let's see, maybe.
Koushik, please use the mic.
See the mode equation of gauge field mode equation, it is depend on J. Okay, so for during inflation, what is happening? Your J increases. If J increases, then
Yeah, I can add on to this one. So basically, if you see this curve, so here you see this parameter which appears in this amplification of the gauge field. So this is indeed oscillating, and this your gauge field will have this nature also. But once you have included inhomogeneities also, these oscillations are suppressed. So yeah, so it's a bit.
It's a trade-off.
Yeah.
So here Axion is your inflation, right? So the
Yes,
and you are doing the simulation only during the inflationary period.
Sorry, can
You are doing the simulation only.
No, we
lattice
are doing
simulation.
simulations for those coupling strength where we can go even end of inflation and few more e-folds after that.
Few
We
more
are only
e-folds.
probing very end of the inflation, not
Yeah, I'm
like,
saying few more e-folds means what? You starting the reheating as well?
yes, yes.
So that means you are also completing your heating dynamics.
If
Is
you
that
see
what?
here in this case epsilon, like this is the result from the simulation and this is the Sorrell parameter.
Okay.
This is the end of inflation and roughly where it becomes 2, you can consider it to be radiation dominated.
Okay.
So yeah, at least in this case it goes.
So is there any other question? So no, I think you should keep it up. Lots of. Okay, so let's move on to our next speaker. Thanks, Ramkishor.